Hello, my name is Stefano Marchidis and I want to welcome you to DD2370 Computational Methods for Electromagnetics. This is the first lecture of the first module. In the first module of this course, I want to cover the basics of electromagnetics and the basics of numerical methods. In particular, this first lecture is about why computational electromagnetics is important, and I want to give you an overview of the basic numerical scheme that we are going to focus on this course. Electromagnetic phenomena have a profound and deep impact on contemporary society and all the technologies that contemporary society uses. In particular, communication devices such as television, radio, internet, mobile telephones, they all rely on electromagnetic phenomena and exploit electrophenomena for communication. So here on this slide there are many different applications that rely on electromagnetics. What is electromagnetics? Electromagnetic field theory, or electromagnetics in short, describe the interaction between electric charges by Maxwell equation. As you know, whenever we have charge, we also have an electric field that tries to either repels or attract a different charge. If the charges are moving, they also create a magnetic field around the current. The Maxwell equation describes the dynamics of charged particles system. Maxwell equations are a system of coupled partial differential equations that relates the sources, the charge, and the moving charge, also currents, to the electromagnetic fields that are the magnetic field and the electric field. In the next lecture, we are going to cover very quickly the Maxwell equation and understand how they couple with the sources. So how do we solve the Maxwell equation and how do we solve electromagnetic problems? Well, there are basically two approaches. The first one is to rely on analytical solution. However, analytical solutions in closed forms are known only for a very limited number of special ideal cases. In particular, often analytical solution cannot directly applicable to real-world application. So real-world application and real-world problems are too complicated. So for instance, we might have a device with a very different configuration and 3D structure that is difficult to describe using analytical model. Instead, to describe and solve problems that are real-world problems, approximations have been used to bridge the gap between theory and advanced real-world application. So for instance, typically our problem is like this hands that is in continuous space. So what we can do is approximate our hands by very small cubes and then solve algebraic equation for each of these cubes. That is an approximation that we try to describe a very complex problem. So the part of electromagnetics that deals with the computational methods and electromagnetics is called computational electromagnetics, in short SEM. So the advent of computers and faster computers changed our ability of Maxwell equations. So what was very difficult and very challenging to solve in the past because of the limited computational resources is now becoming nowadays possible by using faster and faster computers. However, even with the computers at hand, it's still attractive to use analytical simple models to basically validate our approximated solution and to say, well, our approximate solution are good because we are validated with analytical theory that is actually exact. Why SEM is important? SEM allows for a faster and cheaper design process of our electromagnetics device, where the use of prototypes and the testing of prototypes in the labs is minimized. So SEM allows us to understand the underlying dynamics and mechanism of device electromagnetic operation. Right. So with SEM we can simulate real-world device and understanding how actually is working and what are the underlying mechanisms of the device electromagnetic operation. SEM also allows automation of computation for extensive parametric studies. So for instance, if we design a device, we can play We can change very quickly, the configuration, the size of our device, the shape. We can change the material properties of our device by applying a parametric study. So SAM is widely used for electromagnetic design problems. So the design of certain devices for electromagnetics, such for instance antennas. We might want to try a different configuration. We might want to try using simulation. And finally, SAM is also important for basic physics phenomena, to understand basic physics phenomena. So for instance, is widely used for simulation of astrophysical and plasma system. For instance, SAM has been used to identify the Landau damping mechanism, that is a resonance phenomena that happens in plasma, and simulation for the first time allowed to identify the occurrence of Landau damping in plasma. SAM is important for a real-world problem, to understand how to design devices, but also to progress our understanding of basic physics phenomena that entails electromagnetics. SAM is becoming more and more important in both industrial and academic research. SAM is still a relatively young discipline, but still strongly growing. So new numerical methods are year after year progressively developing. So we will cover three basic families, but also what is important to realize that new methods are designed day after day. There are new papers about new methods coming very, very recently. 20-30 years ago, most electrical devices were designed by building and testing prototypes in the labs. The situation nowadays is different. Simulation are replacing prototyping in the labs. Today, the design can be made faster and cheaper by means of numerical computation. SAM has become the main design tool in both industrial and academic research. So labs are still important and there for the validation, but SAM is an additional tool for designing devices. What are the applications of SAM? Well, there is a wide range of applications. We will try to work on some of them during this course. So for instance, SAM is used in designing electrical power engineering systems, such as electrical machines, generators, transformers, and shields for electromagnetic waves. It's also widely used in microwave studies. So for instance, SAM is used for designing microwave networks, and in particular antennas. It's also used for studying what is the plasma behavior in fusion devices, space, and astrophysical system. The performance of SAM is increasing very rapidly for two main reasons. The first one is that the computational capability of a computer is increasing exponentially. You might have heard about this law. This is called Moore's law, that says that the number of transistors per unit of surface is doubling every 18 months. This has been true in the last 40 years. It's slowing down now, but still is growing. So we have to deal with, we rely on faster and faster computers. So we can rely on HPC system and new technologies such as GPUs called accelerators. So performance of SAM is increasing because computers are becoming more and more powerful, but also because there are improvements and developments of algorithms requiring less operation or data movement for same accuracy. Some of them are, for instance, fast multiple methods, advanced spectral scheme. They are all derived from the basic numerical scheme that I'm going to describe in this course. What are the goals of this course? Well, the first goal is to investigate, understand the machinery of SAM, in particular to understand what are the challenges and what are the limitations of the solution that we find for solve this problem. Then we have a very practical goal, that is to apply the most frequently used algorithms in SAM and understand their advantages and also their limitation. We're going to look at three main methods in SAM. The first one is the finite difference and the finite difference time domain technique. The second technique is called the finite element methods called FEM. And the third technique we are going to focus on is called the method of moments, also called boundary element method or BEM. I want to give a brief overview of the three techniques that we are going to focus on this course. The first one is very simple, it's called the finite difference method. The finite difference time domain method is one of the most widespread methods in SAM, often applied to a large variety of microwave problems. Is a straightforward discretization of Maxwell's equation in differential form on a numerical grid. Using the finite difference, the field components of the electric field and magnetic field are discretized on a structured grid of points as unknown. So each point of this grid will host the value of the electric field of the magnetic field. The finite difference method is a very efficient technique because it requires few operations per grid point. Despite the simplicity, the method also has a few drawbacks that we are going to discuss during this course. Well, the first one is that they work well only on uniform Cartesian structured grids. So only very structured grid like this one will provide good approximation of the solution of our problem. And also it's quite challenging to find a formulation to impose boundary condition on the boundary of this numerical grid. So imposing boundary condition might be tricky. The second method we are going to focus on is called the finite element methods or FEM. The FEM is mainly used for time harmonic problems. So when we discretize the equation in the time domain, but also in the spectral domain, this is called the harmonic domain. Finite element methods use a computational region that is divided in a structure grid, so it's not uniform anymore, but it can be a structure and non-uniform. Typically, triangles in 2D are used, or a tetrahedra in 3-dimensional. So in these slides, you see an example of discretization using tetrahedra of a cylinder. So as you can see from this image here, one of the advantages of the FEM methods is that we can describe quite nicely curved surface. See, it can map quite well. This is much better than the finite difference method. However, one drawback is that the FEM is lower in the time domain calculation. For instance, when simple a uniform Cartesian grid can be used and where the finite difference method is very fast. The last and the third method families that we're going to focus on in this course is called the methods of moments or MOM. The MOM is often applied to scattering and antenna problems. The MOM, differently from the time difference method, doesn't use the differential form of the Maxwell equation. Instead, use the integral form of the Maxwell equation. So we will start from integral formulation of the Maxwell equation, and then we'll derive the method itself. The unknowns of the methods are sources, such as currents or charges on the surface of conductors and dielectrics. The method is a true force and very advantageous when problems involve open regions. So for instance, we want to have our electromagnetic waves to go out from the boundary without having any interaction with the boundary. It turns out it's very difficult boundary condition to implement in numerical scheme, and the method of moments provide the cleanest and most elegant approach to solve open boundary problem. So this is the last slide of my first lecture. In the next lecture, I want to cover just the basics of the Maxwell equation, since SAM is basically discretize and solve numerically the Maxwell equation. So we need to know what are the governing equations. Talk to you soon.